There are wooden bridges in America that have been standing for 200 years, through floods, hurricanes, and 2 centuries of traffic, still standing. Modern concrete bridges start cracking in 50. Steel bridges need repainting every decade. But these wooden bridges, built before the Civil War, just keep standing. The secret wasn't the wood, it was the roof. And the reason America's bridges had roofs tells you everything about how different their engineering really was. Now here's the question nobody asks. Why would you put a roof on a bridge? Think about it. You're spanning a river. You need to carry wagons, livestock, people. Adding a roof means more weight, more materials, more labor. It seems like the last thing you'd want. Most people assume it was for comfort. Keep the rain off travelers. Shelter horses in a storm. That's the romantic answer, and it's completely wrong. The roof had nothing to do with the people crossing. It had everything to do with keeping the bridge alive. See, wood doesn't rot from getting wet. Wood rots from getting wet and staying wet, from cycles of moisture and drying that let fungi take hold. An exposed wooden bridge in the American climate might last 10 years, maybe 20 if you're lucky, and the wood was exceptional. But cover that same bridge with a roof and siding, suddenly you're looking at 80 years, 100 years, 200 years if the craftsmanship was right. The math was simple. A covered bridge cost maybe 30% more to build than an open one, but it lasted 5 to 10 times longer. Any farmer could do that arithmetic. Any county commissioner could justify that expense. This wasn't sentiment. This was hard economics worked out by men who understood that replacing a bridge every 15 years would bankrupt a community. And yet here's what gets lost in the history books. These weren't just functional structures. They were engineering marvels built by craftsmen whose names have mostly been forgotten. Men who developed truss systems that modern engineers still study. Men who understood forces and loads through intuition and experience rather than calculus. Today, roughly 750 covered bridges still stand in America. Some of them are still carrying traffic, daily traffic. Cars and trucks crossing timbers that were hewn when James Madison was president. Think about that. We live in an age where a highway overpass built in 1985 gets condemned as structurally deficient. Meanwhile, a wooden bridge built in 1820 is still doing its job. Something happened between then and now. Something was lost. And understanding what these bridge builders knew, really knew, tells you something important about American engineering before the age of replaceable everything. Let me take you inside the mystery of why America's bridges had roofs. The story starts with a problem that doesn't exist anymore. In the late 1700s, America had rivers, lots of rivers, and almost no way to cross them. If you wanted to get goods to market, if you wanted to visit the next town, if you wanted to do basically anything that required travel, you faced the river problem. Ferries were slow and expensive. Fords only worked when water was low. And for 6 months of the year in much of the country, rivers were simply barriers. The obvious solution was bridges. But bridges in America faced challenges that European engineers never dealt with. First, there was the wood. Europe had been largely deforested by the 1700s. Timber was expensive and scarce. American builders had the opposite problem. They had more wood than they knew what to do with. Massive old-growth timber. White pine that grew straight for 100 feet. Oak so dense it would barely float. Second, there was the labor situation. Europe had stonemasons whose families had been cutting stone for generations. America had farmers who needed to get their crops across the river. Skilled labor was scarce. What America had was men who knew how to work wood. Third, and this is crucial, there was the climate. American weather was more extreme than anything English bridge builders had experienced. Hotter summers, colder winters, more freeze-thaw cycles, more humidity, more rot. The first serious American bridge builder to grapple with all this was Timothy Palmer. Born in 1751 in Massachusetts, Palmer started as a millwright. He understood how wooden mechanisms transferred force, how joints could be made to bear tremendous loads, how wood behaved under stress. Now, a millwright in the 18th century wasn't just a mechanic. He was an engineer, a carpenter, and a physicist all rolled into one. He built water wheels that had to capture the energy of flowing rivers. He built gears that had to mesh perfectly, or they'd tear themselves apart. He built structures that had to survive floods and droughts, and everything in between. Palmer brought this practical education to bridge building. He didn't think of bridges as simple platforms stretched across water. He thought of them as machines that had to resist forces, transfer loads, and survive the relentless assault of nature. In 1792, Palmer built a bridge over the Merrimack River at Newburyport. It was a remarkable structure, spanning over 200 feet using a combination of arches and bracing that Palmer had essentially invented. No one had taught him this design. He worked it out through intuition and trial, the same way he'd worked out everything else in his career. But Palmer made a mistake. He left it uncovered. Within a decade, the bridge was showing serious deterioration. The New England weather was eating it alive. The oak was checking and splitting. The pine was softening. Joints that had been tight were loosening as the wood shrank and swelled through endless cycles of moisture. Palmer didn't blame the wood. He didn't blame his design. He blamed his own failure to protect what he'd built. When he got the contract for the Schuylkill Crossing in Philadelphia, he wasn't going to make the same mistake twice. In 1805, Palmer completed what many consider the first truly significant covered bridge in America, the permanent bridge over the Schuylkill River in Philadelphia. The name itself was a statement of intent. This bridge was meant to last. The structure used 3 arch spans, the longest at 195 feet. Palmer braced the arches with a complex web of struts and ties, creating a system that could handle loads far beyond what horse-drawn wagons would ever impose. But the real innovation was what went over it. Palmer convinced the owners to invest in a complete covering: roof, siding, even a coat of paint to protect the exterior. The bridge looked like a long barn stretched across the river. Some people thought it was ridiculous. Why hide a bridge inside a building? Palmer knew exactly why. And he was right. The permanent bridge stood for 45 years before being destroyed by fire, not rot, not structural failure. Fire. The engineering was sound. The covering had done its job. 45 years. In an era when most wooden bridges lasted 15, Palmer's creation nearly tripled the expected lifespan. And it would have lasted longer if not for the flames that consumed it in 1850. Palmer understood something that would become the central insight of American covered bridge construction. The bridge itself, the structural members that actually carried the load, had to be protected from weather the way you'd protect any valuable piece of equipment. The roof and siding weren't decorations. They were preservation systems. Think about it the way Palmer did. You wouldn't leave your mill machinery outside in the rain. You wouldn't leave your tools exposed to freeze and thaw. Why would you leave the most expensive piece of infrastructure in your community unprotected? The covering was insurance. It was maintenance. It was the difference between a bridge that lasted a generation and a bridge that lasted a century. Here's the physics of why this matters. Wood is a remarkable material. Pound for pound, it's stronger than steel in certain applications. It can flex without breaking. It can carry tremendous loads. But wood has vulnerabilities. When wood gets wet, it absorbs moisture. The fibers swell. When it dries, the fibers contract. This cycle, repeated thousands of times, creates cracks. Those cracks let in more moisture. More moisture means fungi. Fungi means rot. Rot means structural failure. Now, if wood stays consistently dry, or even consistently wet, it's remarkably stable. Submerged timbers can last for centuries. Bone-dry timbers can last even longer. It's the wet-dry cycling that kills wood. A covered bridge eliminates that cycle. The roof keeps rain and snow off the main structural timbers. The siding protects against driving rain and splash from below. The interior stays relatively dry year-round. But here's the clever part. The siding was never completely sealed. Builders left gaps, sometimes decoratively, sometimes purely functional. These gaps allowed air circulation. Any moisture that did get in could evaporate. The bridge breathed. This is why so many covered bridges have those distinctive small openings near the roofline, or gaps between the siding boards. Those aren't decorations. Those aren't accidents. Those are ventilation systems designed by men who understood that stagnant air was almost as dangerous as direct rain. The combination of protection from direct precipitation and ventilation for any incidental moisture created an environment where the structural timbers could last generations. But the covering solved only half the problem. The other half was the structure itself. And this is where American bridge builders created something genuinely revolutionary: the truss. That word gets thrown around, but most people don't really understand what it means or why it matters. A truss is a framework of members, arranged in triangles. Triangles are the only polygon that can't be deformed without changing the length of a side. Push on a square, and it becomes a parallelogram. Push on a triangle, and it either holds or breaks. There's no in between. This geometric property makes trusses incredibly efficient. You can span long distances with relatively little material because every member is working, either in tension or compression. Nothing is wasted. But here's what most people miss. In a covered bridge, the walls aren't just walls. The walls are the structure. The truss members that carry all the weight are built into what look like simple wooden walls. This is counterintuitive. When you walk into a covered bridge, it looks like a barn or a shed. It looks like the roof and walls are just enclosing a roadway. But those walls are doing all the work. The floor you're standing on is hanging from the walls. The load of every vehicle that crosses is transferred through those wall members down to the abutments at each end. Understanding this changes how you see these structures. They're not buildings that happen to span rivers. They're load-bearing frameworks that happen to look like buildings. The first major American truss system was developed by Theodore Burr. Burr was born in 1771 in Connecticut, and he combined two different structural principles into something neither could achieve alone. To understand what Burr accomplished, you need to understand the problem he was solving. A simple wooden beam stretched across a gap will sag in the middle. Make the gap wide enough, and the beam breaks. That's the limitation that kept wooden spans short. An arch solves this problem by turning downward forces into outward forces. Instead of the wood bending, it compresses. And wood is much stronger in compression than in bending. That's why stone arches can span such long distances. The stone is always being squeezed, never bent. But arches have their own problem. They want to spread at the bottom. Think of an arch pushing outward at its feet. Without something to resist that outward thrust, the arch collapses flat. Stone arches resist this thrust through sheer mass. Make the abutments heavy enough, and they can't move. But wooden arches don't have that luxury. Wood is light. The abutments would have to be enormous to resist the spreading force. Burr's insight was to combine the arch with a truss. The truss would resist the outward thrust, keeping the arch from spreading. Meanwhile, the arch would support the middle of the span, which is exactly where the truss is weakest. The Burr truss uses a long arch that runs the entire length of the span, combined with a system of vertical and diagonal members. The arch wants to push outward at its ends, which would destroy the bridge. But the truss system resists that outward thrust. Meanwhile, the arch adds strength to the middle of the span, which is exactly where a simple truss is weakest. It's a beautiful piece of engineering. Two systems, each with different strengths and weaknesses, combine so that each compensates for the other's limitations. Neither could work alone at this scale. Together, they could span distances that had seemed impossible. Burr patented his design in 1817, and it became one of the most popular systems for longer covered bridges. Some Burr truss bridges still standing have clear spans of over 200 feet. That's a remarkable achievement for a structure made entirely of wood and held together with wooden pegs. If you ever get to examine a Burr truss bridge, look at the arch. It's not a perfect curve. It's made of multiple layers of timber, bent and fastened together, forming what's called a laminated arch. This construction method allowed builders to create curves from straight timber, and the lamination actually made the arch stronger than a single piece would have been. The lamination technique was itself an innovation. You couldn't get a single piece of timber long enough and curved enough for these spans. But you could take multiple shorter pieces, stack them, bend them into shape, and fasten them together. The grain of each layer ran slightly different, which meant the weaknesses didn't align. The combined arch was stronger than any individual piece. Then came Ethel Town. Town was an architect by training, famous for designing churches and public buildings throughout New England. But in 1820, he patented a truss design that would transform American bridge building. The Town lattice truss is almost comically simple compared to the Burr arch. It's just diagonal planks, crisscrossing each other in an X pattern, connected with wooden pegs called tree nails. That's it. No curves, no complex joints, just overlapping diagonals. And it worked brilliantly. The genius of Town's design was that it could be built by anyone with basic carpentry skills. You didn't need master craftsmen who could shape complex curved members or cut intricate joints. You needed planks, pegs, and a pattern to follow. Think about what this meant for a young country with limited skilled labor. Before Town, building a significant bridge required finding someone with years of specialized experience. After Town, any competent carpenter could build a bridge that would carry traffic for a century. Town actually sold franchises. He licensed his design to builders across the country at $1 per foot of span. For a 100-foot bridge, you'd pay Town $100 for the right to use his pattern. It was one of the first examples of intellectual property licensing in American engineering. Town got rich from these licensing fees. He used the money to travel to Europe, to build a famous library, to establish himself as one of the leading architects of his generation, all from a bridge design that anyone could build. The Town lattice also had a hidden advantage. Because the diagonal members were relatively small and numerous, a single failed piece didn't compromise the whole structure. The load would redistribute through adjacent members. The bridge was inherently redundant. This was important because timber quality varied. Not every piece of wood was perfect. Not every joint was flawless. A design that could tolerate imperfection without catastrophic failure was a design that could be built reliably across a young nation with inconsistent materials and inconsistent labor. Compare this to a stone arch bridge. In a stone arch, every stone is critical. Remove one, and the whole thing can collapse. The Romans knew this. That's why they built so carefully, with such precision. But that precision required expertise that simply didn't exist in early America. The Town lattice traded precision for redundancy. It traded efficiency for buildability. And it worked. There's another aspect of the Town lattice that doesn't get enough attention. The diagonal members don't just carry vertical loads. They also resist what engineers call racking, the tendency of a structure to twist or deform sideways. When a heavy wagon crossed a covered bridge, it didn't just push down. The wheels also pushed sideways slightly, especially on curves or when the horses shifted. A bridge that could resist downward force, but not sideways force, would twist itself apart over time. The X pattern of the Town lattice naturally resists this racking. Push on the structure from any direction, and some of the diagonals go into tension, while others go into compression. The structure stabilizes itself. This is why Town lattice bridges feel so solid when you walk through them. They're not just standing up. They're locked in place in 3 dimensions. The third major truss system was developed by William Howe in 1840. Howe's innovation was to incorporate iron rods as the vertical tension members, while keeping wood for the diagonal compression members. This sounds like a small change, but it was revolutionary. Wood is excellent in compression, but mediocre in tension. Iron is excellent in tension. By using each material for what it does best, Howe created a more efficient structure. The Howe truss also allowed for adjustment. The iron rods had threaded ends with nuts. As the wood shrank over time, which it always does, the nuts could be tightened to take up the slack. A Howe truss bridge could be tuned like an instrument. This adjustability extended the life of these bridges significantly. Instead of joints loosening and the structure slowly failing, a Howe truss could be periodically retightened, maintaining its structural integrity for decades. These three systems, the Burr arch, the town lattice, and the Howe truss, account for the vast majority of covered bridges built in America. Each had its strengths. The Burr was strongest for long spans. The town was easiest to build. The Howe was most adjustable and efficient. What they all shared was an understanding that the covering was essential. You didn't build an uncovered Burr arch or an open town lattice. The system included the protection. The roof wasn't an afterthought. It was part of the design from the beginning. If you ever get the chance to step inside one of these bridges, here's what I want you to notice. First, smell it. Old wood has a particular scent, dry and slightly sweet. That smell tells you the bridge is healthy. Rot has a different smell, musty and sour. Your nose knows the difference, even if your eyes don't. Second, look at the joints. In a town lattice, you'll see hundreds of wooden pegs, each one driven through crossed planks. Those pegs are doing real work. They're not decorative. Grab a flashlight and look at how tight those joints still are after a century and a half. Third, feel the floor move. A wooden bridge is not rigid like concrete. When a vehicle crosses, the whole structure flexes slightly. This isn't a defect, it's the design. Wood bridges are supposed to move. That flexibility is what allows them to absorb loads without cracking. In a concrete bridge, stress concentrates at points and creates cracks. In a wooden bridge, stress distributes through flexure. The bridge gives a little, and in giving, it survives. Fourth, listen. On a quiet day, an old covered bridge makes sounds, creaks and pops as temperature changes, the rustle of nesting birds in the rafters. These bridges are alive in a way that concrete and steel structures simply aren't. The men who built these bridges didn't have engineering degrees. Many of them couldn't have written the equations that describe what their structures were doing. But they understood wood. They'd grown up working it, shaping it, building with it. They knew its moods and its limits. This knowledge was embodied, not abstract. A bridge builder could look at a piece of timber and know whether it would work, could flex a board and feel whether it was strong enough, could tap a joint and hear whether it was tight. We've lost most of this embodied knowledge. Modern engineers work with specifications and calculations. They rarely touch the materials themselves. The knowledge is in the numbers, not in the hands. There's nothing wrong with mathematical engineering. It allows for structures that intuition alone could never achieve. But something was lost when we stopped building by feel. Something human. The golden age of covered bridge construction ran from roughly the 1820s through the 1870s. During these decades, thousands of covered bridges were built across America. By some estimates, there were more than 12,000 at the peak. To understand what this meant, you have to picture the American landscape of that era. Rivers crisscrossed every route of commerce. The Appalachian region alone had thousands of streams and rivers that had to be crossed. Every county seat needed bridges. Every market town needed bridges. Every farm that wanted to sell its produce beyond the local area needed access to bridges. And there weren't enough. In the early 1800s, the shortage of river crossings was an economic crisis. Goods rotted waiting for ferries. Travel times doubled and tripled as people made long detours to reach the few existing crossings. Economic development stalled because moving anything was so difficult. The explosion of covered bridge construction in the mid-1800s was the solution. Communities organized, raised funds, hired builders, and put up bridges as fast as they could. It was infrastructure building on a scale America wouldn't see again until the interstate highway system. These weren't just crossings, they were landmarks. Town boundaries were often described by reference to the nearest covered bridge. Meetings were held under their roofs. Courting couples found privacy in their shadows. The phrase, kissing bridge, wasn't just romantic whimsy. The dark interior of a covered bridge was one of the few places a young couple could steal a private moment. The darkness inside these bridges was intentional, by the way. Horses could be skittish crossing water. The sound of rushing current, the sight of open space on either side, these could spook an animal and cause an accident. The covered bridge solved this by making the crossing feel like entering a building. The horse couldn't see the water. The walls blocked the peripheral view. The animal walked through what felt like a barn, emerging on the other side without ever realizing it had crossed a river. Some bridges even had small windows or gaps in the siding near the entrance, allowing light to help horses adjust before entering the darker interior. The positioning of these openings was deliberate, designed to ease the transition and prevent animals from balking. The bridges also had economic functions beyond simple crossing. Because they provided shelter, they became natural gathering places. Farmers would meet at bridges to discuss prices, exchange news, arrange trades. Some bridges had notices posted inside, serving as community bulletin boards. In an age before telephones or easy mail, the covered bridge was a place where information flowed. You'd cross a bridge and learn that wheat prices had risen in the city. You'd meet a neighbor who'd heard about a job opening 2 counties over. You'd find a notice about a lost horse or an upcoming auction. A few bridges actually had businesses inside. Toll collectors, obviously, but also occasional vendors, repair services, even small shops. The covered bridge was public space in an era when public spaces were rare. There are records of religious services held in covered bridges, political speeches, auctions, even dances. The long, flat floor and the shelter from weather made them natural assembly halls. In some communities, the covered bridge was the largest enclosed public space that existed. But they were also vulnerable. Fire was the great enemy. A covered bridge full of dry, aged timber would burn spectacularly. The draft through the structure would fan the flames. Once a fire got going, there was usually no saving the bridge. Many bridges were lost to arson, accident, or lightning. The Civil War saw deliberate destruction of covered bridges as a military tactic. Burn the bridges, and you stopped the enemy's advance. Both Union and Confederate forces used this strategy. Hundreds of covered bridges were destroyed during the war, many of them centuries old when they burned. The loss was often devastating to local communities. A burned bridge didn't just mean inconvenience, it meant economic isolation. It could take years to raise the funds and complete the construction to replace a lost crossing. Some communities never recovered. Floods were the other killer. The same rivers these bridges crossed would occasionally rise in fury. A massive flood could lift a bridge right off its abutments and carry it downstream. Some bridges were found miles from their original locations, broken and scattered. The mechanics of flood destruction were brutal. Water would rise around the bridge's supporting structure. Debris would collect against the upstream side, creating a dam. Pressure would build. Eventually, something would give. Either the bridge would be pushed off its foundations, or the debris dam would collapse, sending a wall of water and wreckage downstream. Builders developed strategies to resist floods. Extra long spans minimized the number of piers in the water, giving the current less to grab. Strengthened connections to abutments resisted lifting forces. Some bridges were even designed to break apart in a controlled way during extreme floods, with the pieces remaining recoverable rather than being destroyed. There are stories of bridge components being fished from rivers after floods, hauled back to the site, and reassembled. The wooden joinery that held these structures together was sometimes robust enough to survive even the violence of flood destruction. But nothing could protect against every disaster. The attrition was constant. Every decade, more bridges were lost than built. Let me tell you about some of the men who built these structures. Louis Wernwag was born in Germany in 1769 and came to America as a young man. He became perhaps the most celebrated bridge builder of his generation. His masterpiece was the Colossus, a bridge over the Schuylkill at Philadelphia, with a clear span of 340 feet. This was the longest wooden span in the world at the time. Wernwag was obsessive about his craft. He developed new tools specifically for bridge building. He trained crews to his exact specifications. He refused contracts if he couldn't guarantee the timber quality. The Colossus stood for 26 years before burning in 1838. Not a structural failure. The fire was arson, set by someone who was never identified. Wernwag was heartbroken. He'd spent years building something he believed would last a century. It was destroyed by malice in a single night. Nicholas Powers was a Vermont builder who worked later in the 19th century. His specialty was the town lattice, and he refined the design to allow longer spans than Town himself had imagined possible. Powers' greatest surviving work is the West Windsor Bridge in Vermont, built in 1857. At 460 feet, it's one of the longest wooden-covered bridges ever built. And it's still there, still carrying traffic, over 160 years old and doing its job. Powers had a reputation for underpricing his work. He'd bid low to get contracts, then spend more on materials and labor than the price justified. He cared more about the quality of the bridge than the profit. This made him a hero to communities and a headache to business partners. These builders traveled constantly. A skilled bridge builder might work in 5 or 6 states over a career, moving from one project to the next. They brought techniques learned in one region to another. They spread innovations. This itinerant life was hard. Away from families for months, living in temporary camps near construction sites, working in all weather because rivers don't wait for pleasant days. The laborers who worked under these master builders are mostly anonymous. We know the names of the designers, but the men who actually cut the timbers, raised the heavy frames, drove the thousands of pegs, they're ghosts in the historical record. What we know is that the work was dangerous. Raising the trusses was the most perilous part. Massive wooden frames had to be lifted into place, often over rushing water. Falls were common. Men were crushed by shifting timbers. The tools were simple by modern standards. Hand saws, axes, adzes, augers, mallets. No power equipment. Every cut was made by muscle. Every hole was bored by hand. A major covered bridge might take a crew of 20 men several months to complete. The timber alone could take a year to prepare, since it needed to be cut and seasoned before use. Green wood would shrink and warp, loosening joints and weakening the structure. The communities that needed these bridges often contributed labor. Local farmers would help with the rough work, the hauling and lifting. They had a stake in the outcome. This was their bridge, their crossing, their connection to the wider world. When a covered bridge was completed, it was an event. People came to see it. Some bridges had formal dedication ceremonies with speeches and celebration. The bridge represented progress, prosperity, connection. It was proof that the community had arrived. And then, gradually, the covered bridge era ended. The story of why America stopped building covered bridges is really the story of iron and steel. In the 1840s and 50s, iron became increasingly available. Foundries multiplied. Prices dropped. And engineers started experimenting with iron bridges. Iron had obvious advantages. It was fireproof. It wouldn't rot. It could be manufactured to precise specifications in a factory, rather than cut and fitted in the field. The first iron bridges were essentially wooden truss designs translated into metal. But engineers quickly realized that iron allowed for entirely new forms. Suspension bridges, cantilevers, designs that were impossible in wood. By the 1870s and 80s, iron and steel bridges were the standard for major crossings. The Brooklyn Bridge, completed in 1883, showed what steel could do. A wooden bridge could never span that distance. Railroad expansion accelerated the transition. Railroads needed bridges that could carry tremendous concentrated loads, far more than wagon traffic. They needed standard designs that could be prefabricated and assembled quickly. They needed fireproof structures, since locomotive sparks were a constant ignition risk. The railroads largely abandoned wood, and as railroads became the dominant force in American transportation, their preferences became the industry standard. But the death of covered bridge construction wasn't just about technology. It was about economics and culture. Building a covered bridge required local knowledge. You needed to know the site, the available timber, the weather patterns, the community's needs. You needed craftsmen who understood wood. You needed time. Building a steel bridge required money. You could order a bridge from a catalog, have it shipped by rail, and assemble it in weeks. The knowledge was centralized. The skill was in the factory. This transition represented a fundamental shift in how Americans built things, from local to national, from craft to industry, from materials at hand to materials shipped from far away. It wasn't entirely a loss. Steel bridges could do things wooden bridges couldn't. They enabled the modern transportation network. They connected the country. But something was lost. The covered bridges that remained became artifacts of an older way of building, curiosities, tourist attractions. And here's the irony that haunts modern bridge engineering. Those steel and concrete bridges that replaced wooden ones, they're failing faster than the wooden bridges they replaced. Consider this. The average lifespan of a concrete bridge in America is about 50 to 70 years. After that, the concrete cracks, the rebar corrodes, the structure becomes unsafe. The average lifespan of a covered wooden bridge is 80 to 100 years, sometimes much longer. There are covered bridges carrying traffic today that were built in the 1820s. We have concrete bridges from the 1970s that have already been demolished and replaced. Part of this is maintenance. Covered bridges need regular inspection and occasional repair. Replace a few boards, retighten the joints, paint the exterior. Small interventions that extend life indefinitely. Modern bridges are designed for minimal maintenance but finite lifespan. When they reach the end, you tear them down and build new. It's a different philosophy. But there's something deeper here. The wooden bridge builders thought in generations. They were building for their grandchildren, for their grandchildren's children. They used materials that would last because they expected the structures to last. Modern engineering often thinks in budget cycles. What can we build with this year's allocation? When will it need replacing? And who will pay for that? The covered bridge builders weren't smarter than modern engineers. They had less knowledge, fewer tools, more limited materials. But they had a different relationship with time. Today, there are approximately 750 covered bridges remaining in America. Pennsylvania has the most, nearly 200. Ohio, Vermont, Indiana, and Oregon also have significant numbers. Others are scattered across more than 30 states. Some are museum pieces, closed to traffic, preserved as historical artifacts. But many are still working bridges, still carrying vehicles, still doing the job they were built to do. The longest remaining covered bridge is the Cornish-Windsor Bridge, connecting New Hampshire and Vermont. Built in 1866, it spans 449 feet. It's still open to traffic. The oldest remaining covered bridge is disputed, but strong candidates include the Hyde Hall Bridge in New York, built around 1825, and the Haverhill Bath Bridge in New Hampshire, built in 1829. These bridges have survived wars, storms, floods, droughts, and 2 centuries of wear. They've survived because they were well-designed, well-built, and well-protected by their roofs. They've also survived because people cared about them. Communities have fought to preserve their covered bridges. Volunteers have raised money for repairs. Local governments have chosen to maintain rather than replace. This matters. A covered bridge survives only if someone decides, every few years, that it's worth saving. That decision has been made thousands of times across hundreds of communities. It's a form of democratic preservation that no law mandates. Some bridges have been saved by heroic intervention. The Worrell-covered bridge in Vermont was being destroyed by fire in 1993 when locals formed a bucket brigade and kept the flames down until firefighters arrived. The bridge was damaged but survived. It was restored and still stands. Others have been lost despite efforts to save them. Floods have taken bridges that communities desperately wanted to keep. Budgets have forced choices between covered bridges and other needs. Some bridges were simply too far gone when attention finally came. The preservation of covered bridges has become a movement. Organizations like the National Society for the Preservation of Covered Bridges document, advocate, and educate. State-level groups coordinate restoration efforts. Amateur historians photograph and catalog every remaining bridge. There's something beautiful about this. People choosing to maintain these wooden structures not because they have to, but because they want to. Because the bridges mean something beyond their function. What do they mean? I think covered bridges remind us of a time when building something meant building it to last. When craft mattered. When the relationship between worker and work was direct and personal. We live in an age of disposable everything. Products designed to fail. Structures built to minimum standards. Planned obsolescence as business model. The covered bridges stand as rebuke to all that. They say that another way is possible. That durability can coexist with economy. That beauty can be functional. They also remind us of the workers. The men who cut the timber, shaped the trusses, drove the pegs. Men whose names we mostly don't know, whose faces we'll never see. They left their mark in wood and iron. Their work speaks for them across 2 centuries. Every covered bridge still standing is a monument to those workers. Not intentionally. The builders didn't think of themselves as creating monuments. They thought of themselves as solving a problem, getting traffic across a river. But that's often how the best monuments come to be. Not through intention, but through excellence. Work done so well that it outlasts its creators, its culture, its era. 200 years. No concrete, no steel. Just wood, joined right, and a roof. That's the secret. That's why America's bridges had roofs. The roof wasn't about keeping travelers dry. The roof was about keeping the bridge alive. About understanding that protection and structure work together. About thinking in generations rather than years. We've mostly forgotten how to think that way. We build fast and cheap and figure we'll replace it later. Someone else's problem. The covered bridge builders knew better. They knew that later comes faster than you think, and that building right the first time is almost always cheaper than building twice. 750 of their bridges still stand, still carrying loads, still sheltering their trusses from rain and snow and time. Meanwhile, we're inspecting concrete spans from the 1980s and wondering how much longer they'll last. There's a lesson there, not just about bridges, about how we build, how we think about time, how we decide what's worth doing well. The covered bridge builders didn't have our knowledge, our tools, our materials. What they had was a philosophy. Build it right. Protect what you build. Think about the future. That philosophy created structures that have outlasted everything we've put up since. Maybe it's time we learned from it again. If you've watched this far, you understand something that most people never think about. You understand that there's a history beneath the history. That the things we drive past without noticing were built by people with skills and philosophies that deserve remembering. Subscribe if you want to keep learning about the forgotten engineering that built America. Next time, we'll look at another piece of infrastructure you've never thought about, the stone walls of New England, and the back-breaking work of the men who built them. I'll see you then.